algebra with polynomials and rational expressions permeates all of calculus and well beyond that. So polynomials and rational expressions are incredibly important, and being able to effectively manipulate them using your basic properties of algebra is totally vital. So what I'm going to focus on today really is the pure algebra of manipulating polynomial expressions and rational expressions, focusing on the types of problems and things you'll need to be able to do in these lower division courses. So first of all, what's a polynomial? A polynomial is an expression in some number x of a very particular form. So it's an expression of the following form. So a polynomial in the number x, so x is going to represent a number here today, is equal to, well, I'm going to write something which is going to look a little bit strange, a little bit complicated. I want to give you kind of a proper definition, right? So a full definition in complete generality. So a general polynomial in x looks like something of the following form. A sub 0 plus a1x plus a2 times x squared plus dot 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 plus a sub n x to the n. Now this is quite a sophisticated way to write it down, and this is how you would write it down at university level. Let me talk through various aspects of this. First of all, these a sub 0, a sub 1, a sub 2 up to a sub n, those are just constants, right? Fixed numbers. It could be 1, pi, 6, minus 12, it doesn't matter. It's a fixed collection of numbers. You're thinking about x in a sense as being a variable, right? Because it could take many potential values. But a0, a1, a2 up to an, those are all fixed constants. So these guys, fixed constants. Dot, dot, dot. Real numbers, they're called coefficients. So constant real numbers. I'm going to do everything with real numbers as always. So just decimals, called coefficients. So a polynomial expression in x is something, it's a number that looks like this, and the numbers a0, a sub 0, a sub 1, a sub 2 up to a sub n, those are called the coefficients. So we think about x kind of as a variable, as I said, because it's just a stand-in for any number at the end of the day. This is kind of a variable. So it's just a stand-in for a number. Just a stand-in for a number. Okay, so a few things to be said. This n is important. So n is going to be some non-negative whole number. Okay, n could be 0 and you just have a0 at the front. N could be 1 and it would go up to a1 times x. I'm ignoring writing a 1 here because x to the power 1 is just x. I suppose if you want to be crazy as well, you could write in here, you could write kind of an x to the power 0 if you wanted, but that's just equal to 1. That's the reason we don't bother including it, just to make it all really uniform. Okay, but if the top term, so the biggest term here, if an is not equal to 0, so that's not guaranteed by the way I've drawn this. If an is not equal to 0, then we decree that this polynomial expression has degree n. Degree equals n. So a polynomial has a degree. So it's kind of the biggest power of x that turns up. If an was equal to 0, it'd be kind of stupid because we could throw it away. But just from the way I've written it, it's not guaranteed. Okay, so the degree of the polynomial is some sort of piece of information about it. And polynomials with certain fixed degrees have kind of specific names historically. So if n is equal to 0, so if it's degree 0, Well, as I said, that basically means all you've got is the constant term. So none of this is here. So you're just literally a fixed constant. So this would imply the polynomial expression is constant. It doesn't matter what x is. So just for example, it could be the number 3, okay, or 5 or -1, it doesn't matter. So not terribly interesting. If n was equal to 1, it's a bit more interesting. If n is equal to 1, then we say it's linear, for reasons that we'll see later on when we're doing functions. But linear, as an example, you could write this, I don't know, 4 plus 2x. That's an example. Or 4 minus 2x doesn't make any difference, because minus 2x is plus minus 2 if you want. So that's an example of a linear polynomial expression in x. We could keep going. The only one that really matters to us beyond this should be n is equal to 2. And if n is equal to 2, this is what we call a quadratic. Something you will have definitely seen before, I'm sure. Okay, so as a quick example, I don't know, 2 plus x minus x squared. So just to really make sure we completely understand what's happening here, in this case, so can I zoom out a little bit so we can see all of this? In this case, what have we got? We've got a0 is equal to 2, a1 is equal to 1, and a2 is equal to -1. Now, something to say here is I'm writing this in a format which maybe is a little bit different than what you're used to. Often when you write polynomials down, you write them from the biggest power of x to the lowest power of x. So I'm not doing that up here, because if I try to write a general polynomial from the biggest power to the lowest power, it's kind of ugly, because the numbers, it would be an minus 1, an minus 2. It would be counting down, so the coefficients would be labeled backwards. But for really low degree polynomials, it's not a huge deal, right? So I could easily write this in a more familiar format, perhaps. So I can write this in the form, well, your kind of ax squared plus bx plus c form. So you could write this as x squared, or should I say, minus x squared plus x plus 2. You can rearrange it freely. Okay, why doesn't it matter? It doesn't matter because of the commutative property of addition. A plus b is equal to b plus a. So you can freely move things around. Okay, so polynomial expressions are incredibly important. They're going to provide the kind of foundational example of things called functions later on in the course, which are going to be what you're going to be studying in calculus and other courses. And as I said, understanding the basic algebra of dealing with polynomial expressions is incredibly important. We'll deal with rational expressions in the next video. So first of all, imagine I have two polynomial expressions and I want to add them together. So it turns out that addition of polynomials is quite simple. Remember, a polynomial is just a number when it comes down to it. It's just a number written in a very specific format. So if we're talking about adding polynomials, that makes complete sense because we're just adding numbers. But addition of polynomials is very simple, really, from an algebraic perspective. So I'll just immediately tell you the thing you need to be worrying about. So addition of polynomials I mean, really all it is matching and adding coefficients. So I'll show you what that means in a second. Matching and adding coefficients. So let's make this a little bit neater. So very important. Oh dear. So matching and adding of coefficients. So what do I mean by that? Well, let's take two polynomial expressions and let's add them together. And let me just show you what I mean. So example, All right, let's take two polynomials. Let's make them the same degree just for simplicity. Let's imagine 2 plus 3x plus x to the 4. So when I write x to the 4, it really is 1 times x to the 4. I'm just suppressing the notation. Plus minus 1, let's say minus x, plus x cubed minus 3x to the 4. Okay. So this is a big string of numbers, right? And I want to rewrite this as a polynomial expression. That's my basic plan here. I don't want to leave it in this kind of expanded format. The reason being, I can kind of see there's overlap. Like, for example, there's a linear piece here. There's a linear piece here. And there is a degree 4 piece and a degree 4 piece. So if I want to write this as a polynomial expression in x, I need to kind of gather those terms together. So let's take the time to do that. So first of all, what I'm going to do is, I'm going to really labour the point here, I'm going to write both polynomials completely fully. So, for example, the first expression doesn't have a quadratic piece, it doesn't have an x squared piece, but in a sense it does, it's just 0 times x squared. So if I write this completely out fully, what would it be? It would be 2 plus 3 times x, so I'll just really carefully write it properly, then 0 times x squared, there's no 0 term, there's no cubic term, and then of course there is 1 plus x to the 4. So this is me really expanding the first piece. Well, let's do the same for the second. So minus 1 plus minus 1 times x, there's no quadratic piece for the second guy, plus 1 times x cubed, is that correct? And then finally plus minus 3 times x to the 4. Okay, so this feels agonizing, but I want to go through this just incredibly carefully to make sure that we really understand why addition of polynomials works the way it does. So what I'm going to do now essentially is I'm going to match up the equivalent pieces. We've got a constant piece here, a linear piece, degree 1, a quadratic piece, a cubic piece, and a degree 4 piece. So I can freely move these sums around. A plus b is equal to b plus a. So it makes sense to try to match these up because they've got a very similar format. So let's do that. So if I do that, what do I have? Well, I'm going to end up getting the following. So the first piece would be 2 plus minus 1. Okay, great. The next piece would be 3 plus minus 1. In fact, let me be really careful about this. I want to do this incredibly carefully for you. So 3 times x plus minus 1 times x. Is that correct? Yep. Then plus 0 times x squared plus 0 times x squared. So I'm just bunching this together. Then plus, so I think I'm going to shrink this down so it's all in one line. So give me a moment. I'm going to make this a little bit smaller. Then plus, what's it going to be? Plus 0 times x cubed plus 1 times x cubed. And then finally 1 times x to the 4 1 times x to the 4 plus minus 3 times x to the 4. So I'm really doing this ridiculously carefully. So each step I'm just being super duper careful about all of the algebra. So really all I'm invoking here is the fact that I can rearrange the sum, right? Like I said, a plus b is b plus a, so I can move things freely around in the sum. So I've moved the constant terms together, the linear terms, the quadratic terms, and so on and so forth. But now notice something really useful happens. Because of this, I have the distributive property. So the distributive property now will allow me to pull out a factor of x from the first, for example, a factor of x squared from the second, x cubed from the third, x fourth from the fifth. So that means I should be able to write these in a much more close to polynomial format. So let me write this out fully again. This is 2 plus minus 1 plus, 3 plus minus 1 all times x plus 0 times x squared plus 0 plus 1 times x cubed plus 1 plus minus 3 times x to the 4. Okay. So now in this case, what do we know? Well, now I just need to work out what all of these things in brackets are. So in brackets, what do we have? We have 1. So going to be a 2 next. Don't want to make a mistake here. So let me make this large again because we have plenty of room. So now this is equal to 1 plus 2x. Is that correct? Yes. Plus 0 times x squared. I won't bother including it. Plus 1 times x cubed. I won't bother writing the 1. Plus, it's now 1 plus minus 3. That's minus 2. Minus 2 times x to the 4. And now I've written it in polynomial format, right? It's exactly the correct format. So really what we've done here is exactly what I've said above. We are taking the polynomials and we are matching the coefficients. So that's what I'm doing here. This is me matching the coefficients and then just adding them up essentially, and those are the new coefficients. So you've got to be careful, and like the main thing to understand here is that you need to kind of fill in the holes, right? If there's no x cubed term or x squared term, whatever, you need to include it, but as 0 times it. So here, let me just kind of fill in some details. At this point, we're using the distributive law or distributive property, just to really hammer this home. We're using the distributive property. Yeah, so this is the basic idea, and I think it's pretty simple. It's the kind of thing that once you've done quite a few examples, as I'm sure you have in the past, you can do this fairly quickly. But it's good to do it incredibly methodically, at least several times in your life, because it reinforces the basic algebraic steps. Right, so when I do this summing, I do think through each step, right? It does flash through my mind, oh, I'm moving this around. I can do that because a plus b is equal to b plus a. Oh, I'm invoking the distributive property. I don't really think about it too consciously, but it's kind of there in the background. And that's what you need, right? To really deepen your understanding of algebra, is to make sure that every time you're doing algebra, it's kind of, there's a background concept, a simple principle you're invoking at each stage. Okay, so what about multiplication? So multiplication is a fair bit more difficult, as I'm sure we all know. So multiplication of polynomials. So multiplication of polynomials, it's kind of cruel. It's not what you might guess. So for addition, all it was you just paired up coefficients and added them. So there's a terrible trap that everyone falls into when they first learn about polynomials, which is it's not what you guess. You would guess the product of polynomials would be you just pair up the coefficients and multiply them. That sounds logical, but actually if you're going to invoke the laws of algebra, it just completely fails. So instead, really what this is repeated application of the distributive law. I said before that the distributive law is kind of the most important thing practically when doing algebra. It's like you use it all the time. So the distributive property. So it's a little bit of a vague thing to say. I'll show you an example in a second. But you absolutely definitely know this has to be the case already, because we've already done an example, basically, where you are doing this, namely when we FOIL. So if I take two linear polynomials and multiply them together, that's the sum of two things multiplied by the sum of two things. We know that that multiple is more complicated than you might expect. So this is just foiling. This is this FOIL acronym for products of linear polynomials. It's got to be. So we know that FOIL came from the distributive property applied several times. It's going to be just more of the same, basically. So let's do an example. So I don't want to go too crazy, but let's do one that kind of illustrates the point. Imagine if I have to multiply 1 plus x, a linear polynomial, by a cubic polynomial, let's say 1 minus 1 plus 2x minus x cubed. So the aim of the game is to rewrite this as a polynomial expression. So the first thing I'm going to do is I'm going to kind of treat this as a fixed number, if you want, and then I'm going to treat these as two different pieces. So this is going to be like the distributive property, and I'm going to get the following. So the first application of the distributive property would be, this is equal to, I'll really write it full, it'll be 1 times 1 plus 2x minus x cubed plus x times 1 plus 2x minus x cubed. I know this has to be the case because this is the distributive property, right? So what we're invoking here, I'll just write it down really carefully. This is just a statement that a plus b times c is equal to a times c plus b times c. Right, remember these expressions represent numbers. That's how numbers work, so we can't just wishfully think something occurs. It has to be one of my core properties of how algebra works. But next, well, I can distribute again if you want. This one isn't terribly interesting because you're just multiplying by 1, but this one, you're multiplying by x. So that can distribute in with all of these three terms. So this would give me what? So this would give me, nice and simple, 1 plus 2x minus x cubed. And then when I distribute by the x, it would be a plus x there, plus 2x squared, because of the x times x, minus x to the 4. So I'm going quite quickly there, but the principle is the same. So at this point, this to this, in fact, let me do this in a different color just to highlight. So these are exactly the same. What's the principle I'm using? Well, I'm just using the distributive property, but in a slightly different format, right? I'm using the fact that a times b plus c plus d breaks apart as a times b plus a times c plus a times d. Okay, so it's the distributive property just with three terms in it, right? Makes no difference. But then I'm basically summing up polynomials at this stage, so I'm just going to gather the terms together. So I'm not going to go through every agonizing detail here. There's only one constant piece. There's linear piece coming from there and there. So 2x plus x is 3x. Quadratic piece, one quadratic piece, it's the 2. I got this correct. So one quadratic piece, that's going to be the plus 2x squared. One quadratic piece plus 2x squared. A cubic piece, one cubic piece minus x cubed. And finally, I've got 1 degree 4 piece minus x to the 4. So we did, in this case, I suppose, the distributive law, or a variant of it, 3 times, basically. So you can imagine if you're multiplying together bigger polynomials, you've just got to do more and more and more. So multiplication of polynomials is a laborious task. it's something you don't want to do by hand if you have an enormous polynomial. Something to say here is be incredibly methodical and slow about this. Don't try and second guess things. Keep every stage simple. And be very, very careful about transcription errors. So what I mean by a transcription error is accidentally changing things on the way down. So in my original notes that I'm actually looking at now, I've made one of these transcription errors. So what I mean by that is accidentally writing something like this here. Right, so that's definitely wrong because whatever I'm doing, that has to be the same as that. So I've made a mistake there, right? And it's actually in my original notes. I'm looking at it right now. That's wrong. Now, these transcription errors are really important. They're one of the major reasons people mess up questions when it comes down to it. And a big reason for making them is, first of all, just losing concentration a little bit, which is easy, especially if you're going quickly in some sort of test type environment. But a big reason for writing things as carefully as this is if you do make a transcription error, so you drop a sign or something as you go from one stage to another, you can spot where the mistake has happened. So if I basically have a negative there, and then I do everything correctly down from that point, if I get to the bottom like, oh, something's wrong, I look to the top, I'll be able to see this is the first time this problem turns up. So doing things this carefully is incredibly important from that perspective, especially when you've complicated calculations. If you can't go back through and work out exactly where the mistake is, you're in big trouble. I suppose it's the same principle as writing good code so that you're able to find some sort of mistake, some syntax error. If you just jump from the beginning to the end with no intermediate steps, it's hopeless, right? It's impossible. So I've made this mistake myself. It's very easy to make this mistake. Desperately try to avoid it. And it requires concentration, right? When you're doing these, you need to make sure at every moment you're looking at it and thinking, okay, is this equal to this? Yes or no, yes or no, yes or no. Simple to make a mistake. Okay, so this process, so we can add and we can multiply polynomials. Addition is quite straightforward. Multiplication is more complicated, of course. Can we go backwards from this multiplication? So this is a really interesting problem